Welcome back to part 3 of the circular motion lesson. So when we just left off a moment ago, we had developed this rather important formula for centripetal acceleration as negative omega squared multiplied by the position vector. Note the negative sign meant that our acceleration is in the opposite direction to the position vector r. Now, we had from earlier that omega equaled v multiplied by r. Let's go back and check that. We had that, sorry, other way around, that v equaled omega times r. There it is, equation number 1. Time to bring that one back. V equaled omega times r. So it would seem that omega equals v divided by r. I'm going to use that to substitute. Now I should note none of the terms in this equation here are vectors. These are the magnitudes of the speed, the magnitude of the radius, and the magnitude of the angular. There's no directions involved in those. So if we come back to here, our acceleration vector equals negative v squared over r squared. That's instead of omega squared. And I now have to multiply by my radius vector. And you might be tempted to think I can cancel this with one of these r's, and you're on the right track, but we need to prepare that slightly first, because we can't really cancel a scalar with a vector. But what can I do with my position vector? I can consider that to be a scalar value r multiplied by a unit vector. So remember, the hat notation doesn't just apply to basis vectors I and j. We can have a unit vector of any vector. And basically the unit vector was the original vector divided by the modulus. So that is a vector of length 1 pointing in the direction of the radius. Now the scalar at the front can quite nicely cancel here to leave divide by r. Let's write that neatly. The acceleration vector equals negative v squared over r, those are scalars, multiplied by a unit vector which is in the direction of the radius vector, the position of the particle. So this part over here, r hat, is just to give the direction. It's almost like here, when I split this up, I split this as magnitude multiplied by direction. A unit vector, of course, by definition, has length of 1. Now, that's well and good. In physics, you've probably not been worried too much about these direction vectors. You've probably simply taken the modulus of the acceleration, just a, and then you wouldn't worry about the direction r hat, and you probably wouldn't even worry about the negative sign. You'd just write v squared over r. Both of these are correct. In fact, this one is more correct because it's a vector equation. It's not really more correct, I'm just trying to teach the physics people. So a vector equation there, of course, has to have directions accounted for. This one here, not a vector equation, still correct. This is just the scalar values. The magnitude of the acceleration is the speed, the magnitude of v squared divided by r. And that's a pretty handy rule to remember when doing some problem solving. But the real fun, of course, was up here with the vector calculus that we had in lesson 2. And hopefully that will show you where some of these formulas that you may have been learning in physics have come from. All right, thanks very much. That's the end of that little bit, and I'll see you in the next video.